So next week's homework will be the very last one, and it finishes at section 10.6. So it's kind of missing all the hard stuff, but that stuff will show up on the exam review, so you'll have plenty of practice with it. Okay, where were we? So we were doing section 10.6 yesterday. We got through a decent amount of it. This is just talking about power series. The way of thinking about power series is you just have a polynomial, which is one of the most common kinds of functions that show up in this class. And then you just do an infinite sum instead of a finite sum. So it just goes on forever. And so we looked at power series. So this is a power series centered at 0, but it can have more general power series where you have like a power series centered at some point C, which has the following form. It's kind of the same thing, except now you have an x minus C that you're taking the power of consistently. And so I guess like the primary question we were asking ourselves is whether or not power series converge or not, and finding the interval of convergence. So when talking about intervals of convergence, the top of page 2 is really important to look at, as well as just knowing how to work through examples. So the main idea was that if we have the following, if we have that f of x, this power series f of x converges absolutely on this interval of convergence where we have the distance between x and c is less than r. What this means is that if you wanted to write this out in interval notation, I think this was a source of confusion yesterday, is we take this c, which is the center of our series, and then we add and subtract r from it to find the interval of convergence. So if you have like the absolute value of x minus c is less than r, writing this out in interval notation, the interval of convergence is going to be c minus r. So the center minus the radius will be the left endpoint, and then the right endpoint is going to be c plus r, where the c again is the center of your series, and then r is the radius of convergence that you found using the ratio test. So we went through one example yesterday, or we went through 2 examples, I think. I think we went through 2 examples. This one, you just use the ratio test. We found that absolute value of x had to be less than 2. So the interval of convergence is going to be minus 2, 2. You can also write it or think about it in the following way. This is really x minus 0. So the center is 0. So you do 0 minus 2, the center minus the radius, and then the center plus the radius, which is where this minus 2, 2 came from. The other example was a bit more interesting. We had to be a little bit more creative in terms of how we wrote out these intervals, and we had to include an endpoint as well. So after applying the ratio test for this last example we went through yesterday, we ended up finding the following inequality. So we ended up finding that the absolute value of x minus 5 had to be less than 4. And so this is saying that the distance between x and 5 has to be less than 4. So you can think in terms of, well, we can have like any number greater than 1 and less than 9 would fit the bill. But again, you can think of the center of our series is 5, right? That's where this, like we have this x minus 5 to the n. So the center of the series is 5. And then the radius was 4. So to find the interval of convergence, you do the center 5 minus 4, which is where this 1 comes from. And then you do 5 plus 4. Again, the center plus the radius gave us this 9 here. So that's how you determine the interval from this inequality involving the absolute value. I didn't say, I was like rushing towards the end of class yesterday, so I didn't say it as explicitly as I probably wanted to. So this was the final answer, was this interval from 1 to 9, and we include the 9 because when we plugged in x is equal to 9, we ended up getting a convergence series by the alternating series test. Okay, so that's just reviewing yesterday's lecture. Are there any questions before moving on? Okay. Yeah, so now there's just a couple of other applications or techniques where we need to learn to work with power series. I guess like a big question is going to be, if we're given a function, what is its corresponding power series going to be if it has a power series in the first place? And that's really what 10.7 and 10.8 is going to focus on. Like we'll be given a function that has infinitely many derivatives, or like it's infinitely differentiable. And then we'll be able to create something called a Taylor series, which will be a power series representation of that function. And it gets a little bit complicated, but we already know some power series, right? Geometric series are really just kind of an example of a power series, for example. So let's look at geometric series and then use the geometric series we know to express other functions in terms of their power series. Right, so if we have a geometric series, it's going to look like something of the following form. Usually you have like a c times r to the n, but we're just assuming c is equal to 1 here. And so we have the following formula for a geometric series of the form of just summing Rn to itself. This is going to be 1 over 1 minus r. Again, this is just the geometric series equation we've used frequently throughout the last couple of days or last couple of classes. So you need to know this formula. This is really just the c over 1 minus r, where c is equal to 1. And so we know that this is going to be a convergent series when the absolute value of r is less than 1, i.e. when the ratio is less than 1, it converges. And so if we write x in place of r, we end up obtaining a power series expansion where the radius of convergence is going to be r is equal to 1. Right, so this is going to be the power series expansion for this function 1 over 1 minus x. Right, so we have 1 over 1 minus x. This is just equal to the sum of these powers of x. Right, so it's like 1 plus x squared plus x cubed forever. And again, this is just a geometric series, so this isn't anything new that's going on. We're just recontextualizing the geometric series we've been thinking about already. And so what we want to do is we're going to take this power series that we know already, and then we're going to derive equations for other functions and their power series. So we're going to modify this equation to find other power series expansions. And so this is where stuff gets, I think people generally find this kind of hard, or they can. So it's like worth paying attention to this. So for this, it wants you to find the power series expansion with the center c is equal to 0 for f of x is given by 1 over 2 plus x squared. And it wants you to find the interval of convergence of that power series. Okay, and so what we're going to want to do in this situation, and you'll have some homework problems where you need to do this, is you're going to take this 1 over 2 plus x squared, and you're going to transform it into something of the form of 1 minus 1 over, or 1 over 1 minus x. And so what this means is we're just going to take this 1 over 2 plus x squared. It's kind of vague the way I just worded it. But like one thing we can do is if you look at this series or like this function versus the function we have here, we're starting off with a 2 when it should be a 1. So the first thing we can do is we can factor out a 2 from the denominator. So this is really equal to 1 over 2 times 1 plus x squared, which you can actually just rewrite as 1/2 multiplied by 1 over 1 plus x squared. And then what do we want to do from here? The next thing we can note is that we have, when comparing 1 over 1 minus x with 1 over 1 plus x squared, we have a minus sign here and a plus sign here. And so you can rewrite this in a clever way. You can rewrite 1 over 1 plus x squared as being equal to 1 minus negative x. Oh, I messed up. I should have factored out. I forgot to, if we're factoring out a 2 in the denominator, it should be x squared over 2, right? So that way, when we multiply through by 2, you actually end up getting 2 times 1, which is just 2, and then 2 times x squared over 2 would give you the x squared. I forgot to do like the x squared over 2 here. Just like it was just an algebraic error. Okay, and so we can rewrite 1 plus x squared over 2 as 1 minus x squared over 2. And so why do we want to do this? Is now, if we do a little bit of a substitution or a change of variables, like we do for integration, we'll end up getting a function that looks exactly like this 1 over 1 minus x. So the function that we're going to make a substitution for is we're going to let u be equal to minus x squared over 2. So we have u, we're going to let u be what's inside of this parentheses. So it's going to be minus x squared over 2. And so if we make this substitution, hopefully it'll be apparent why we made this substitution. So this is going to be equal to 1/2 multiplied by 1 over 1 minus u. So the reason why we make this substitution is now it's clear, right? This 1 over 1 minus u is exactly like this 1 over 1 minus x that we have. And we know what the power series expansion of 1 over 1 minus x is. And so now we just apply this formula to this 1 over 1 minus u. And the only thing that changes is now it's going to be u to the n instead of x to the n. So it's pretty much the exact same thing. So this is going to be 1/2 multiplied by this infinite series. So going from n is equal to 0 to infinity of u to the n. Again, this 1/2 is just a constant, so you can just leave it outside if you want. And then from here, you have to substitute back in. Like your answer should be in terms of x. So now we'll substitute back in for u. So this is equal to 1/2 times the series from n is equal to 0 to infinity. And now it's going to be minus x squared over 2 to the nth power. And so we're going to go a little bit further than this. I'm not really sure on the homework assignment how far it wants you to go. But in general, you want to write with as much detail as possible. So if we have minus x squared to the nth power, this is really the same thing as having minus 1 to the n multiplied by x squared to the nth power, right? Because we have a minus 1 multiplied by x squared, so you can distribute the power. And then this is over 2 to the nth power. And then we have a 2 outside, like we have a 1 over 2 outside of the sum, so you can do 1/2, or like this 1 over 2 multiplied by like this 1 over 2 to the n. So this is really going to be equal to the following. So this is going to be equal to n is equal to 0 to infinity of minus 1 to the n, x to the 2, or x squared to the nth power is just x to the 2n. And then we have the 2 times 2n, so it's going to be 2n plus 1, like this. And so this is what the power series expansion will end up being. And so most of the work just comes from these initial steps. You're given this original function, and then you want to simplify it in a way so that way you can rewrite it in the following form, usually with a different variable. So it's like 1 over 1 minus x. We're able to transform this 1 over 2 plus x squared in terms of this 1 over 1 minus u, where u is equal to minus x squared over 2. So that's finding the power series, and then it wants you to find the interval of convergence. Before I do that, are there any questions about how I found the power series? Okay, and there'll be some homework problems on this, so you'll have more practice. It's like one of those things you just need to do practice with. But they all kind of play out in a similar way. So we want to find convergence for this sum. We want to find convergence. We're just going to use the ratio test. You want to use the ratio test pretty much anytime you test the convergence of a power series. So we're going to do the ratio test. So we're going to be looking at the limit as n goes to infinity of the n plus 1th term of the sequence over the nth term of our sequence. And we could ignore, again, I say this over and over again, but with the ratio test, you're doing the absolute value. So you don't need to care about the minus 1 over n. You can exclude it. It doesn't make a difference. So this is going to be the limit as n goes to infinity of x to the 2 times n plus 1 power over 2 to the n plus 1 power. And then this is all over x to the 2n over 2n plus 1. So you have to be careful. You have to make sure it's like 2 times n plus 1 and not just 2n plus 1. So it should be 2n plus 2 and not 2n plus 1. It's like a point where like it's easy to make a mistake there, right? Like we have to substitute the n with n plus 1, so it should be 2 multiplied throughout n plus 1. And so this is going to be equal. Now you can just do the ratio test. Things will cancel out nicely, and you'll be able to determine the interval of convergence. So this is really going to be x to the 2n plus 2 over x to the 2n multiplied by 2n plus 1 over 2n plus 2. So a lot of things end up canceling out with one another. This is the limit as n goes to infinity. So x to the 2n plus 2 over x to the 2n will just give you an x squared. And then if you 2 to the n plus 1 over 2 to the n plus 2 will just give you a 1/2. So there'll be a 1/2. And the n is completely gone now. So like the limit doesn't really do anything. So I'm just going to get rid of the limit So for this to converge, this has to be less than 1. So now it's just a matter of multiplying both sides by 2. So this implies we have x squared is less than 2. Then you can take the square root of both sides. So absolute value of x has to be less than the square root of 2. So you end up getting the following. And I guess you have to test for the endpoints, but the endpoints end up not converging. And I kind of want to move on to something else. So I'll just tell you, like, it ends up being this interval after testing the endpoints. Okay, any questions about this example? Like any part of this example? Okay, yeah, so you'll have more practice with this on next week's homework. And I guess so, I mean, it's a pretty common kind of problem, so it'll probably show up on the final exam as well. Okay, so that's one way of going from like knowing the power series of one function and then getting the power series of another function just via this algebraic manipulation. Next, we're going to look at how we can use derivatives and integration to go from one power series to another power series. And luckily for us, doing derivatives and integrals on power series works as you would expect it to, and that it goes term by term. So what I mean by this, it's this theorem 2 is what I'm referencing. So if you have this power series centered at x is equal to, or a power series centered at c, given here, with the radius of convergence given by some r greater than 0, then it turns out that the power series is going to be differentiable on this interval. Furthermore, we integrate and differentiate term by term. So what I mean by this is if you look at this function, this power series, if we take the derivative of this power series, and you want to determine what the derivative is, you just have to take the derivative of the term inside of the series, right? So the derivative of this is just going to be the derivative of a n times x minus c to the n. And so you just use the power rule, right? So you bring the n down. So you have n multiplied by an times x minus c, and then you subtract the power by 1. So it's just the power rule. You're technically doing it for every single term in the sum, but in terms of like how you represent it in summation notation, you do it in the following way. And that's the same idea for integration as well. You integrate term by term. So if you wanted to integrate this function, again, you just use the power rule for integration. So you'll take the power, add 1 to it, and then divide by n plus 1. Everything else stays the exact same. And then you just have to remember that you have to add by a constant, right? So like there's this is like really like the integral, and then you have like the plus c, but they write it as a, I guess because it's a power series, I guess. Yeah, and so like these derivative series and integral series end up converging via the same radius of convergence, which is really nice. And so we're going to use differentiation and integration to go from one power series to the other now. So that's what these last two examples are. This first example, we're going to use the derivative. The second example, we'll be looking at the integral. So for this next example, we want to prove that for x between -1 and 1, we end up having that 1 over 1 minus x squared ends up being equal to 1 plus 2x plus 3x squared plus 4x cubed plus 5x to the 4th power. And I guess if you wanted to figure out like what you should be doing, because I think the hardest part, like if I tell you to use the derivative to deduce like what the power series is going to be, I wouldn't say that's the hard part. The hard part is like if I gave you this problem on the exam without further context, like knowing that you should use the derivative to determine what this power series is going to be. I think like knowing how to do it is the hard part, or knowing that you should be using the derivative in the first place is the hard part. So like how you can tell you should use the derivative here is you should be looking at this part of the series, right? So they give you the terms term by term. We have like this 1 plus 2x plus 3x squared. And it looks kind of close to something that we've already been looking at. I mean, we've only looked at like one explicit power series so far, or maybe like 2. Does anyone see like how you would, maybe this is like a hard question, but does anyone see like how you'd be able to get this series based off of like another power series that we're familiar with, or one that we like were just looking at like 10 minutes ago? Yeah, Morgan, were you raising your hand? Mm-hmm. Never mind. Okay. Oh yeah, Liam. Yeah, so we're taking a derivative, right? So if you look at this power series that we were looking at before, right, we know the power series of 1 over 1 minus x is equal to x to the n. So writing this out explicitly, this is equal to 1 plus x squared plus x cubed plus x to the 4th forever. And so if we took the derivative of this function, this would be equal to 1 plus 2x plus 3x squared plus 4x cubed, and so on and so forth. So you can see that this series here is really just the derivative of this series that we already are familiar with, right? So like this is really just equal, like this term here is equal to the derivative of x to the n, where n is equal to 0 to infinity. And then we know that this is equal to 1, or this is equal to the derivative of 1 over 1 minus x, right? So we really just like, all we really need to show is that if we can show that the derivative of 1 over 1 minus x is equal to 1 over 1 minus x squared, then we would actually be done with this problem, right? And so this is kind of like the note here, like this is the key observation, is if we take the derivative of 1 over 1 minus x, you want to use the quotient rule. We can probably do it in another way, but I feel like most people are familiar with the quotient rule. So this is equal to the derivative of the top minus the bottom, or multiplied the derivative of top times the denominator minus the top times the derivative of the denominator. And then this is going to be over the denominator squared. So this will be 1 minus x squared. So this ends up just being equal. So this derivative is 0. So you get 0 minus 1 multiplied by the derivative of 1 minus x, which is just minus 1. So this numerator just ends up being equal to 1. And so this ends up being 1 minus x squared. Okay, and so you kind of already see, like we have the derivative of 1 over 1 minus x is equal to this, which is equal to this, which is equal to this. So we're done with the problem, but I'm just going to write it out in a single line. So we have 1, what we just showed is we have 1 over 1 minus x squared. We showed that this is equal to the derivative of 1 over 1 minus x. We know 1 over 1 minus x has the following power series. So this is the series from n is equal to 0 to infinity of x to the n. So it's just the derivative of this thing. And then going term by term, this is equal, which is the sum. When we're taking the derivative, you start at n is equal, like if you're starting at n is equal to 0, you then go from n is equal to 0 to n is equal to 1, because the derivative will cancel off the first term. Something to be mindful of. And so this will be times n times x to the n minus 1. And then if you look at what the series ends up being equal to explicitly, just like writing it out, this will be equal to 1 plus 2x plus 3x squared plus 4x cubed. And then it just goes on. Right? So we're able to show that 1 over 1 minus x squared ends up being equal to this power series that they end up giving you. And it's really just by using the derivative again. Okay, so you have to be, I think just knowing to use the derivative is kind of the hard part, which is why I spent a lot of time just saying like how does this relate to something we already know? And it's via the derivative, right? Okay, any questions about this example? Yeah, Katie?
On like a test, do we have to like show like the bottom line, or can we just like leave it at the top?
Yeah, I mean, you could, if you already have that this is written out, like you have this equality here, and then you show that this derivative ends up being equal to 1 over 1 minus x squared, then like it's pretty, yeah, then you don't have to write out like this part here, I would say. Because then you already are saying like this is equal to this guy here. So like the equality is proven, yeah. I was just doing it just to make sure we're on the same page, just like summarizing everything pretty much. Okay, any other questions? Okay, so we looked at the derivative. Now let's look at integration. So the next one's a little bit more difficult, I would say. But this is like the go-to example whenever you want to use integration to find power series. So for this one, it wants you to find the power series of inverse tangent. It wants you to show that inverse tangent of x ends up being the following. And then this ends up being equal to x minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7. And we'll find another way to derive this later on, but I think this is the easiest way of deriving like this power series. Okay, and so this is kind of another one where it's difficult to tell you should be using integration, I would say here. But I guess I'll see if anyone can kind of give a reason. No shame if not. I think it's kind of hard to tell you should be using integration. Does anyone see why using integration would give you an easier way to determine what the power series of arctangent would end up being equal to? And yeah, Kyson. Yeah, so you want to, I would say, like, you want to think in terms of, I want to see if I can explain without giving away. Like, you want to think in terms of like which function is going to end up having an integral that ends up being equal to arctangent, and then that function, integrating part by part, will give you something that looks like this after you put it in power series. So I don't know. I feel like it's hard to explain without just giving it away. Any other last shots before I just explain it? Okay, yeah, so the key idea is the following. The reason why we want to use integration to determine what the power series of inverse tangent is going to be is we end up having that, like, arctangent can be written in the following way. So we have inverse tangent of x. This is equal to the integral of 1 over 1 plus x squared dx. And maybe it's like still up to, it's like, well, why are we, I still don't understand like why we're looking at this, but this is like 1 over 1 plus x squared. It looks a little bit like 1 over 1 minus x. If we just do a little bit of manipulation like we were doing before, right? And so it makes sense to, and I guess you kind of have to remember that the derivative of inverse tangent is equal to 1 over 1 plus x squared to use this, which makes it additionally difficult. But when we write it out in this way, we can then think in terms of like, what's the power series of 1 over 1 plus x squared going to be? And then we can integrate term by term, and we should end up getting the following series here is the idea. So I could do all this like in a single line just by writing 1 over 1 plus x squared in terms of like this integral, but I'm going to write out a little bit more. So let's investigate. We're going to investigate 1 over 1 plus x squared and see what happens. So we have 1 over 1 plus x squared. Again, we want to compare this. We want to compare with 1 over 1 minus x, because we know that this is equal to x to the nth power, like the sum of x to the n. And so just like we did for the previous example, really the only big difference we have is we have like this plus instead of a minus. So we want to rewrite this as 1 over 1 minus x squared. And so this is where like the alternating signs are going to end up showing up here, like the minus plus minus plus. And so now we're going to let u be equal to minus x squared. That's why I did it outside of the integral. Because if I did it inside of the integral, it looks like I'm doing u substitution, which I feel like would make things confusing. And so this is really equal. We can write this as being equal after making the substitution to 1 over 1 minus u. And so 1 over 1 minus u is equal to the sum from n is equal to 0 to infinity of u to the nth power, where u is equal to minus x squared. So this is going to be equal to the sum from n is equal to 0 to infinity of minus x squared to the nth power. And then we can rewrite this as being equal to the sum from n is equal to 0 to infinity So we have a minus 1 to the nth power multiplied by x squared to the nth power. So this is minus 1 to the n multiplied by x squared to the n, which you can write as x to the 2n. Okay, so this is the power series expansion of 1 over 1 plus x squared. The reason why we want to do this is now we can write arctangent is equal to the integral of this power series. And then we just need to integrate term by term. And then we'll end up finding that it ends up being equal to this series. So this will be equal. So we end up having that inverse tangent of x is equal to the integral of 1 over 1 plus x squared dx. This is equal to the integral of this sum. So n is equal to 0 to infinity of minus 1 to the n times x to the 2n with respect to x. And so this is going to be equal. So now we just integrate term by term. The only variable we have is this x to the 2n. So it'll be x to the 2n plus 1 over 2n plus 1. So this is going to be, wait, hold on. Oh, yeah, this is good. This is good. So this is going to be minus 1. The only thing I'm like tripped up about is like what the sign ends up being. I think here, this is how I write it out in my notes. So I do n is equal to 1 to infinity. Like the hard part, I think, is just making sure like the sign actually ends up matching up with like the sign that's given to you in the beginning. And there's like multiple solutions or ways to do this. I just want to be consistent with what I have written down in the solutions. So this ends up being equal to minus 1 to the n minus 1, which I'll explain because I feel like that's probably confusing people. And then when you're integrating, it's going to be x to the 2n plus 1 over 2n plus 1. Okay, so the reason why I changed this is I needed to make sure. Oh, wait, hold on. Wait, I'm messing this up. Maybe I should write it. Yeah, this is where I'm getting, okay. It's like the indices are messing me up. Because if I left it as is, if you plugged in n is equal to 1, the first term would be x cubed over 3. So, I wrote it as minus 1 in my notes. Okay, so if you do it this way, okay. If you write it this way, you'll end up getting the correct thing. Because then if you plug in n is equal to 0, you'll end up just getting just x, which matches what we have here. When n is equal to, oh wait, oh the sign is still, okay. This is messing me up so much. I'm gonna write it in this way. My apologies. But then I feel like that kind of takes away the intuition of the integral. Okay, if you write it this way, then it ends up matching. But then I feel like it looks confusing because they're doing like, it should be like 2n plus 1 over 2n plus 1. Wait, what if I wrote it like, sorry, I'm like, this is the right answer. Like this gives you the right answer. You can check going like term by term. If I want to write it out as like x to the 2n plus 1 over 2n plus 1, which I think if you just did minus 1 to the n, I think it actually ends up working out. So I feel like I was like overcomplicating things way too much. Yeah, this would work. I don't know. I was like thinking way too much about things. I mean, they're the same series at the end of the day, but I was like, I don't know. I was like, the sign was like throwing me off so much. Okay, and so you can check and see, like this ends up being equal. Like if you plug in n is equal, let's look at this guy. If you plug in like n is equal to 0, you'll get x. When n is equal to 1, you'll have minus x to the 3 power over 3. Then when you plug in x is equal to 2, you'll get x to the 5th power over 5 minus x to the 7th over 7. I would say like ignore this thing. This is like the one you should be thinking of. I just wrote it this way in my notes. And I feel like it's not like the good way of understanding things. So focus on this one. They're the same series at the end of the day. I just like changed the index and it has like the following effect. But this is like the more intuitive version. Yeah, so sorry about that was like a bad explanation at the end. But I feel like the important part is like the first half. Okay, any questions about this example? Yeah, so like going from here to here, like it took a lot of time explaining it. All that really happened was I was just doing the integral of x to the 2n which is like x to the 2n plus 1 and 2n plus 1. And it didn't change like the actual index at all. So like the minus 1 to the n's all stayed the same. This is like a really unintuitive way of writing things out. Oh, there's actually one part. Well, I messed up explaining this problem. There's one other part I actually missed out here, right? We did the integral, so there should be a plus a at the end, right? There should be a constant. And so we actually need to solve for what this constant is. It's the problem that never ends. Okay, but to determine this constant, so what we found out is the following, is we have inverse tangent of x is equal to this series right here. And then the key observation is if we let x be equal to 0 in this series, everything is going to go to 0 except for this a. So a is just going to be equal to inverse tangent evaluated at 0, right? So we have inverse tangent of 0. This is equal to 0. It's by trig stuff. This is going to be equal to a plus 0 minus 0 plus 0, which is equal to a. So we end up finding that a is equal to 0. So you end up getting exactly what I had written before, but I wanted to make sure if it shows up on the homework, you know how to find what the constant ends up being equal to. So we end up getting this is like x minus x cubed over 3 plus x to the 5th over 5. What I had written above, right? But now you know how to find constants as well. Okay, any last questions about this example? Yeah, Katie.
Why can't you just get rid of the n minus 1?
Oh, is that like going from here to here?
Yeah.
Or yeah, so it's like all I did was to shift the indices by 1. Like you can start at n is equal to 0. If you start at n is equal to 0, you can think in terms of like this would be minus 1 to the 0th power, and then x to the first power, and then this would be over 1. If you shift everything over by 1 on the index, it has the effect of subtracting here by 1. So for instance, if you plug in like n is equal to 1, you would have minus 1 to the 1 minus 1 would be equal to 0. So like these terms would then match with one another. And then if you plug in n is equal to 1 and to 2n minus 1 here, you would have x to the first power, which is the same thing you would get if you just plugged in like n is equal to 0. It's kind of confusing, I would say, like keeping track of the indices, but all we're doing is like, if you change the starting index, it allows you to rewrite terms in a different way. So like these sums are the exact same, but like the way of expressing them is different because we're starting off at a different initial value. But it's like kind of, yeah, it's not something I want to focus on too much in this class, I guess, because I think it gets like, I mean, I was getting tripped up on it pretty hard, as you can see. Okay, any other questions before moving on? Okay, so that was it for section 10.6. So there's only 2 sections left that we're covering in this class. There's section 10.7, 10.8. 10.7 is kind of like an interlude between 10.6 and 10.8. So like the only reason, I shouldn't say the only reason, like the big reason we're looking at power series is we're going to introduce Taylor series. Where like Taylor series is a particular kind of power series. But before going into like Taylor series, we're going to look at Taylor polynomials. So that way we can develop an intuition about like why we care about Taylor series. Like we'll find that Taylor polynomials give you really good approximations for functions that have like a sufficient number of derivatives. And then the Taylor series will give you like a perfect approximation because they're like you're taking a limit as n goes to infinity of the partial sum you're taking into consideration. So that's like the big idea. Like we're talking about power series, so that way we can eventually talk about Taylor series, and that's what this class finishes on. And that's like section 10.8. And so like we're really in 10.8 is really just combining 10.6 and 10.7 together. Okay, so we're going to talk about Taylor polynomials. And I think this is going to be a really important section if you want to understand what's going on in section 10.8. Like a lot of the formulas in 10.8 are all derived or all come from section 10.7. So you need to understand 10.7 to understand 10.8. And so this actually kind of goes back to like a section in Calc 1 that we didn't spend that much time on, and that's linearization. So that was section 4.1. This is like the first time we've talked about linearization since section 4.1, probably. At least in my class, like it was on the exam a little bit. But this idea for linearization was it was giving us a way to approximate a function that was close at a point X that was close to a point A via the tangent line. So like this linearization we were looking at is really just the equation of the tangent line of a function at a point X is equal to A. And where this linearization equation comes from is this from the equation of the determinant, or not determinant, the derivative. So like this is the equation that we have for the linearization function. Like it's this equation L of X is equal to F of A plus F prime of A multiplied by X minus A. This is really just coming from the equation, like the derivative equation. So this is F prime of A is equal to the limit as X goes to A of F of X minus F of A over X minus A. And so if you took this equation, well, like right here, we're looking at a limit. If you look at values of X that are sufficiently close to A, what this means is like, we're not looking at a limit. Instead, we're going to say F prime of A is almost equal to this quotient whenever X is close to A, right? That's what the limit's doing, is it's formalizing, saying like, we're getting really close. So this gives you an approximation of F prime of A. And now if you solve for F of X, what this would look like, I wasn't planning on deriving this, but I'm gonna do it anyways. So I don't really have the space, but this is like the same thing as having X minus A multiplied by F prime of A is approximately equal to F of X minus F of A. And then if you add over the F of A, you have X minus A multiplied by F prime of A plus F of A is approximately equal to F of X. Right, so this is Calc 1 stuff, section 4.1, but this is where this linearization idea comes from. And so this linearization idea is actually kind of like it's like a confined or like constrained version of the Taylor polynomial. So this is actually an example of a Taylor polynomial of order 1. So what we can do with the Taylor polynomials is we're going to add on to this approximation by incorporating higher order derivatives. And the more higher order derivatives that we end up incorporating, the better approximation we're going to end up getting. So that's the intuition behind what we're doing. So like these Taylor series, like these Taylor polynomials, in essence, give you a way of approximating pretty much any function as a polynomial. And polynomials are the nicest functions to work with. So that's kind of like the magic of these Taylor polynomials. And then if you go from a polynomial to the series, like it's no longer an approximation. It's like the exact same function. Okay, so that's like the intuition behind what's going on. So like this linearization idea was really just like a Taylor polynomial of order 1. So this is like a first order approximation, and this is only really useful in a small interval around X is equal to A. So the goal of this section is we're going to look at higher order derivatives, which will give a better approximation on a larger interval. So this picture summarizes what we're going to be pursuing in this chapter, or these last two sections. So we have this original function F of X. If we look at the linearization is just the equation of the tangent line at X is equal to A. So it's just this line here. And so if you incorporate the second derivative into this linearization, you end up getting the second order approximation. And so you can see it's no longer a straight line. We instead get a quadratic function that kind of almost matches the curve that we have with y is equal to F of X. And so you can go into, like, after doing the second order approximation, you can do like a third order, fourth order, and it'll get closer and closer. And we'll look at an example and graph out a couple of examples to see exactly what's happening. Okay, so I only have like 2 or 3 more minutes. I'll go into like the definition of the Taylor polynomial, and then we'll call it a day and pick up there tomorrow. And so what follows, just some terminology that's going to come up. We're going to assume that F is defined on an open interval. And we're going to assume that every single derivative ends up existing on that interval, which is a pretty big assumption. There's like a lot of functions that don't have like the kth derivative defined on each point of the interval. But a lot of functions we like do, like e to the x, cosine, sine, all those derivatives exist. So we can apply these ideas to functions we like. And so we say two functions f and g agree to order n at x is equal to a if their derivatives up to order n at x is equal to a are equal. So what this means is like g approximates f to order n at x is equal to 0. If we have f of a is equal to g of a, the first derivatives agree to one another, the second derivatives agree with one another, and then all the way up to the nth derivatives agree with one another. And so we're going to be looking at a specific function g that approximates f, which is on the next page. And so this is where we're going to continue in class on Wednesday, is we're going to be talking about the nth Taylor polynomial of f centered at a. So this is going to approximate our function f to the degree n. It's given by this formula that we'll derive. So this is where we'll pick up tomorrow, probably get through this section and then go through 10.8 on Monday.